Hello everyone, I'm Spiros Mallios. I am from Greece, as with the rest of my Altair colleagues, Panos and Spiros. My role in Altair Engineering is I'm a business development manager in the digital twin technology. Today I'm going to get the chance to present to you two of our topics related to AI-powered engineering. And we're going to start by a short presentation of PhysicsAI. Before we start, has anyone of you used or played with PhysicsAI before? Because I know it's quite a new software in our portfolio. Is anyone experienced with PhysicsAI? No? Has anyone seen... okay, Simon. Has anyone seen a presentation of PhysicsAI before, or is it something completely new to you, this topic? Some have seen, okay, all right. So, under the... It should... this point. No, it's not. All right, now it's working. All right. So my colleagues have talked a lot about the left-hand side of the slide here, so how we are modeling basically our world, our physical world, based on equations, physical equations. And as you all know, we have the preprocessor, the solver, and the post-processor. Basically, the preprocessor is trying to write down these equations, and the solver is then integrating these and give you the contour and the results you want. So instead of only relying on this approach here, we see more and more the adoption of a combination between the equation-based approach and the data-based algorithms. And we as Altair saw that coming quite a few years ago, so we have acquired some companies also in the data world, but a lot of our tools are built in-house. So PhysicsAI and ROM-AI, which I'm going to talk in the next slide, are tools native for us. We build them. They are built by engineers for engineers, so this is important because we always keep in mind that it's engineers who are going to use these tools, not data scientists. And we are proud to say that in, let's say, the... Oh, come on. No. Should be that way. In this field, we have the most broad portfolio since we can handle a lot of algorithms, let's say. So we are going to see some examples together, but in the AI world, you can have a lot of algorithms that are going to read the data for you and basically try to take some decisions. Maybe I'm going to use this one since it's quite faster. All right. So it's this slide is from last year, but it's actually announced a few days ago that even we continue to be in the Gartner Magic Quadrant, the leaders. So basically what we are showing here is that Altair is, in terms of the visionaries and in terms of our ability to execute, on the top right-hand side, which actually means a lot to us because it recognizes us as a key player in the business of data and artificial intelligence. And it's something that you can use as, let's say, reassurance that, okay, we are certified by third parties in this domain. So, a little bit into the details of what we're going to see today. When you want to engineer a part, when you want to design a part, there are two main ways that you can look of it. You can either look into the details, into the component level, and this is where you are basically in the conceptual phase trying to design a part and understand how it's going to look. You want to know if it's going to fail, if it's going to handle the temperatures, all this kind of stuff. And on the other hand, this part is going to live inside a system. It's going to interact with other parts. It's going to interact with the environment. It's going to cooperate with other components. So we have tools that are going to help you in both design phases. On the first here's part of the presentation, my presentation, we are going to cover the left side, PhysicsAI, and on the next presentation, after some colleagues, we're going to see ROM-AI, which is more into the system level and digital twin applications. Now, what are the, let's say, the heart behind all of these technologies? Why is the AI name behind all these technologies? We want to use the leading technologies in trying to understand and get value out of our data. And of course, we are using artificial intelligence algorithms, neural networks, more in specific. And depending on the application, different architectures of the neural networks are employed. So what you see on the left, written with GDL, stands for geometric deep learning. It's a technology that has emerged in the last years that is trying to understand basically from the geometry, from the shape. And on the right, we have ROM-AI, which is a combination of dynamic system theory and the classical deep learning. We're going to see more about it later. So let's jump into PhysicsAI. Why is PhysicsAI different than all of the other solutions, let's say, in the market as of classical traditional ML approaches? We read directly the CAD. So we directly use the geometry or mesh, if you have, and we learn from the CAD, we learn from the geometry. So you don't have to, the biggest advantage in this, you have to think is that you don't have to parameterize your model. You don't have, meaning parameterize, you don't have to say, okay, this is my length, this is my diameter, this is my radius, this is something specified. We just read arbitrary shapes. And the benefit, the other benefit of PhysicsAI compared to the traditional ML approaches is that it will give you the results on the contour, so the field prediction, not just some key points or some KPIs. So more into that. This is where I like this slide a lot because it actually allows people to graphically see when to use PhysicsAI versus other machine learning methods. And we can see that, okay, the left side is basically where this is what you already have. You might already have run a DOE, maybe in hyperstudy. So you might already have structured data, meaning that, you know, I changed a couple of parameters. I varied the thickness, the length again, the material properties. Or you might be in a situation where you have a lot of data lying around from simulations from ages, from past designs, which are totally undocumented. And if you're in this scenario here, the only way to go forward with AI is with PhysicsAI, because PhysicsAI can work on both structured and unstructured data. Whereas traditional ML approaches need to have structured data, need to have labels, need to have, you should have already, let's say, pre-processed the data heavily in order to use it. So basically, PhysicsAI is allowing you to use historical data from your past simulations. And what you can do with this, why would you do that? Well, the main benefit is that you get a solver with your own data that is running in seconds. So instead of waiting for solvers to converge, I don't know, in hours, minutes, or days, you have instant physics predictions in seconds. So that's our key differentiation here. Now, of course, the prediction, as we said, can be in whatever form you want. You can have just scalar outputs, meaning I have a stress value that high. It can be a whole curve prediction. It can be field, predict the whole contour. Or as my colleague Panos showed with a little bit with expert AI, you can also have, let's say, a classification. So you can judge, you can have an eye of an expert engineer built inside this software that is going to say to you, okay, this solution is passing the criteria and this solution is not. So it allows you, let's say, to be more efficient in the decision making. So how does PhysicsAI process the geometries? Basically, it just reads information about the nodes. It's our intellectual property. There are a variety of codes implemented to do this as efficiently as possible. But what we do in the end is we try to interpret what is the change in the geometry and what this change translates to the whatever results you have. Now, when I mean whatever results you have, I'm actually literally speaking, because you could translate this to stresses, temperatures, electromagnetics applications, CFD, or even, let's say, the total cost that would be required as of tooling. So if you have, let's say, a subtractive manufacturing process, you can even predict the cost of tooling with this kind of methods. So this is a full slide, but let me try to guide you through what a typical process with PhysicsAI looks like. And we always start with data, right? We need to have some training data. This data typically comes from historical simulations. So you might have already run a bunch of simulations. Or this data can also be what we call synthetic. Synthetic means that we have generated this data through some DOEs, design of experiments. And as my colleague Panos mentioned, there's a very strong coupling with PhysicsAI and our software, our hyperstudy software, our design of exploration software, where you can basically, this is an image from hyperstudy, you can basically run in an automated way a lot of design variations. Now, once you have this data, you can use this data to train a solver, and you can do this either locally or in cloud. Now, we would suggest most of the customers to start first locally and see how things are progressing for them, how fast is the simulation, how fast is the training. But once you get to larger assemblies with millions of elements and thousands of simulations, then we typically see the customers are switching into Altair 1 because of the availability of multiple GPUs, and the training time is cut down drastically. So once you have the model trained, basically the next step in order to make sure that your solver, the solver that you build is robust enough, you need to validate it, and this is this step here. And we typically validate our solver with some unfamiliar test. So you don't validate a solver with the same data that you have trained it with. We don't validate it with this data. We validate it with a completely different data set, something that the solver hasn't seen, the PhysicsAI, so that we can make sure that we have a generalizable model. Generalizable means that it can predict unknown, unfamiliar situations. And then, of course, we can use this for real-time exploration. And this is real-time is actually a true word, and something that a lot of people are, let's say, interested is why would you use PhysicsAI versus, let's say, some traditional FEM approach, or in the end, is PhysicsAI going to replace the traditional FEM approach? The answer is no, it's not going to replace it. We want to give fast predictions in order to guide to a direction, not use it for final validation. Always, the final validation will be an FEM solver. We are not going to completely remove the maths. We want to have a tool that the engineer has right in his hand that is going to tell to him, okay, if you do this change, your design is going to be better or worse. That's the intention of this. It's not the intention is not to just get this and say, okay, now I'm manufacturing the part. No, you're not going to do that. Maybe in 10 years where we have thousands and thousands of experience with this kind of projects and trust, yes, but right now, this is an asset for the engineer to use it to guide through the design. So instead of relying on some, let's say, instinct, internal instinct, of, oh, I will do this and the part is going to perform better, you have a, let's say, a tool right next to you which is going to run in seconds. That's the main goal here. So the previous example was a classical FEM model with stresses. As I told you, this technology can be applied to virtually any application. So here we have a high pressure casting. Now in this kind of applications, you want to avoid porosity. You want to avoid having air inside the casting. And air can be, let's say, introduced by an improper design of the mold. So you might not have improper gate sizes. The solidification process might be too quick. And basically, the idea is that you need to have a proper mold design. So the same thing here, exactly the same process. We have training data with previous simulations, both on the filling and the solidification of the high pressure casting. We use it to train the PhysicsAI solver, and then we can get the fast predictions, the fast recommendations of how should I change my mold design in order to reduce the porosity. All right. So let's here talk a little bit about the main concerns of most of the users on using this technology. Apart, let's say, from the fact that PhysicsAI can run locally, so you don't have any kind of fear of leaking data or anything, the next concern of users is, how do I know that my model is predicting well? And for that, we have a bunch of error KPIs, error measurements. The most used one is the mean average error, which is basically the average error between the prediction of the PhysicsAI solver and the actual results. And this is very useful, again, on the testing set, on some unfamiliar data. And the biggest asset, I think, which is available to the user is this confidence factor here, this confidence score, which basically tells you when you want to predict a new design with PhysicsAI, how much confidence should you have in the actual prediction. Now, how is this done? This is basically a, let's say, similarity score between the new design that you want to predict and the old design. And it's going to very fastly tell you that, okay, I have been trained to predict this kind of new design, or, you know, what you are inputting here is completely new to me. So what we typically say is that, let me change that again from here. What we typically say is that whatever is above 0.7 is a good metric, and you can be you can trust the new prediction. So this is a nice visual here. There is a duck and a wolf, so you can understand that if you are trying to predict some similar shape of ducks, it's going to perform well. Now, if you trained it on ducks and you want to predict a wolf, it's not going to predict well. So you can see that the confidence factor is minus 450. It's going to say to you, okay, I can give you some predictions, but you shouldn't trust them at all. All right, so let's see a nice example here from, this is actually from a white paper that we did. It's available online. You can read the full article, the full white paper in detail. Now this is, this comes from the aerospace industry. It's one of the biggest, let's say, the most common needs in the aerospace industry is to validate your FEA model, your design, based on some test that you've done on the actual constructed plane. So a typical, let's say, typical process is that they place a lot of strain gauges inside the wing, inside the structure of the wing, and basically with some realistic loadings that the plane is seeing, they are getting what they call the shear moment diagrams. So basically, what are the shear moments, torques, and stresses inside the wing structure. And what is the goal here? The goal is to identify what would be the loads applied on the wing, which of course you cannot measure from the air, from the actual air, based on the measured data from the strain gauges, from the measurements that you have on the test data. So how can we help with PhysicsAI on this application? We basically do the same, have the same workflow here. We have lots of simulations with different wing shapes and different wing loadings. So the loadings here are varied. These here loadings on the interface nodes are varied. And we train a model that is going to predict here the shear moment diagram, these curves here, basically. Once we have a model that can predict based on the forces and the wing shape, the shear moment diagram, we can use this model to do basically the reverse thing. We can input a new curve, and we can ask our solver, okay, what would be the loads that are going to equate to this? So basically, you have the plane, you are doing some online testing, you get the data from the strain gauges, and then in a matter of seconds, you can calculate what would be the loadings applied. So, okay, basically what would be the loadings applied on the wing. Why is this useful again? Because if you didn't have this technology, you would have to manually run or let an optimization run, which would take days or weeks, of varying all these loads on the airplane wing, one by one, until you found what could be the combination that is giving you this curve, which is a lot of, it's a lot of time consuming, of course. All right. I have another example here with, again, in the aerospace and defense industry, where a very common need in, let's say, the electromagnetics field is to predict the radar cross-section. Now, the radar cross-section is basically an indicator that is saying to you how detectable an object is to radars. So, of course, this is very relevant to the defense industry because they want to create stealth combat airplanes. And you can imagine that there are numerous design variables that change and influence this RCS, this radar cross-section. And if you want to vary all of this, you would need a lot of time to run the whole, let's say, DOE and learn from the space here. So basically, PhysicsAI, what it does, it's using historical simulations from, again, previous runs, based on different shapes of aircrafts, different wings span, different torsion angles, etc. And with exactly the same process, we can get a model that's going to predict this radar cross-section for some new aircraft design. Again, the same workflow. As you can see, we follow exactly the same steps. Now, another application, this is a customer application here from Ford. I wanted to add this just to show something public. Unfortunately, we have very few public use cases from customers since it's, most of them are quite, let's say, reluctant to share what they find with this. But in any ways, this is something that Altair, that Ford Brazil shared with us, and it shows that they can benefit a lot in predicting the body-in-white torsion stiffness, basically from hours to seconds here. And as you can see, the contour results are pretty much matching between the two images. As you can imagine, Ford had lots of previous designs already stored in the database. They were in a structured format. We don't care. We can use it without any problem. So for 2025, I'm going to show two slides that are showing what are the updates versus the previous releases. In any case, you guys, as you told me, haven't used it already, but in case you start using it now, there are, compared to last year, there is a new neural network architecture behind PhysicsAI, which is called Transformer Neural Simulator. And as you can see, the main benefit is that you can get much more smoother results in the prediction, and both in crash results and on external aero CFD. So it resembles more closely to what you would expect from the physical scenario. And what I would say that is the biggest benefit of this new architecture is that it's quite insensitive to the mesh, to the coarseness of mesh. So here is, let's say, a comparison between the previous architecture and the new architecture of PhysicsAI. And you can see that in all of these three designs here, the results match the ground truth much better than versus the older architecture, which is, as you can see, very sensitive to how good the mesh is. So here it's quite the same, but on these two, let's say, scenarios, you see that the predictions are quite far off from the ground truth. So these are some very nice additions from our solver team in Altair. So to finish off this presentation, I would like to sum up here a little bit our AI portfolio and where we are going at. So you might have heard about the generative AI, the term generative AI, which is basically, or Gen AI, as people call it, which basically means that we see that in the future, and we are working towards that, you will have the machine actually tell you where your part should go, where your design should go. And of course, this cannot be applied if you don't have a fast prediction solver. So inside this, we see that our technology is going to lie. And I would say that in the coming years, we will have some big breakthroughs through this area here. That's it. Please, I'm open to any questions, but I would encourage you. I know that it's quite new topics for you guys, but please register to our e-learning courses. Both of the trainings for PhysicsAI and ROM AI are around 3 to 4 hours. They're quite fast. You will be able to use it, I believe, right after the training, and it's free. So there's no excuse of not enrolling it. All right, thanks, guys.